To AMIT GATE classes. In the last class, we have seen how to calculate time complexity of all those problems where iteration is involved. Today we'll see asymptotic notation. Before we'll have a detailed discussion about asymptotic notation, let me rewind few things. One thing is what? If I have a program, let's say main, and if there is no loop involved, if no loop is there, doesn't matter how many lines are there, the complexity we are always going to write order of 1. I don't mind how many lines are there in this program, complexity is always going to be what? Order of 1. Second, in this program, if I say I have one for loop that is going to run 1 to n, I have another for loop that is going to run, let's say, 1 to m. Let me take it n only, and after that, let's say in between I have 100 sequential line. So ideally, if I'm going to calculate the complexity of this program, the complexity of this program ideally is going to be this 100 line is going to take 100 amount of time, plus this is an independent loop which is going to take n time. This is an independent loop which is going to take n time. So ideally I should write 2n plus 100. As I told you, we are supposed to ignore all smaller term as well as we can ignore all constant value, because 100 is nothing but we can write as constant. This 2n can be 5n, can be 100, and I don't mind. The only leading term is what? N. So whenever you are getting these kind of complexity, I can directly write order of n, because this constant has no value. This is always going to be constant. So I can directly write what? Order of n. Now, today we'll see what is asymptotic notation, what is the worth of having asymptotic notation. I hope if you're watching my lectures daily, this is going to be cakewalk for you, because once you understood how to calculate complexity, everything is going to be cakewalk for you. Now, there are various notation to represent complexity. One is big O, big omega, theta, small o and small omega. This big O is used for worst case representation. I'll let you know what is worst case. This big omega is used for best case, and this theta is known for average case. Now, what is best case, what is worst case and average case, and which complexity we are supposed to bother while writing program or algorithm? Now, let me take one example, and through that example, we'll try to understand what is worst case, what is best case, what is average case. Now, let us say I have an array. In this array, let's say I have n elements, 5, 6, 8, 2, 3, 4, let's say 10. 1, 2, 3, 4, 5, 6, 7. 7 elements are there in this array. How many comparison I need to do to search any element in this array? Let us say this is the how to search any element in the array. We'll try to compare with the first element. If we'll be able to find that element in the first attempt, that's fine. Otherwise, we'll try to compare with second value, then third value, and so on. So this is the process for searching. This is called linear search. Now, worst case means what? If I have 7 elements, how many comparison I need to do to find one element from this array? Worst case means what? Nothing can be worse than this. That means if 7 elements are there, in worst situation, I will find this element at the last. If my element is at the last, how many comparison I need to do? I need to do 7 comparison. This is the worst case. Similarly, if I say in this array, if n elements are there, if I am going to search any one element from this array, in worst case, how many comparison I need to do? N comparison. Maybe I'll get my luck is not good. I will get that element at the very last. That is called worst situation. So how many comparison it is going to take? Definitely n comparison. So worst case is what? How much time my program is going to take under worst situation. So worst situation is supposed to be calculated in this fashion. This point is clear enough? Now think reverse. Best case. Best case is what? I have an array of, let's say, 7 elements. I'm looking for one element. If my luck is very high, I will get that element in the very first attempt. So this, how many comparison I required in this case? In that case, one comparison. So I can write that in best case, how many comparison is required? One. Now, whenever you are representing any complexity in the form of worst case, you need to write big O, and then you need to write what? Complexity. That's why while doing a calculation of all iteration based problem, I used to write order of n. Order of n means what? This program is going to take n time. This capital O is representing what? Worst time. That means this program under worst situation is supposed to take how much time? N unit of time. Now, whenever you need to represent best case, you are supposed to represent in this fashion. If something is written in this form, omega 1, that means the best case of this algorithm is constant. Now, if something is written in this form, omega n, that means in the best case, my algorithm is going to take how much time? N. This point is clear enough. Now, third thing which is very, very important. Third thing is very, very important because most of the people are having this confusion. What is average case complexity? See, this is just a notation. How to represent worst case, how to represent best case. Now, let us say I have one array where all the elements are, let's say, sorted. The elements are already sorted. Now, tell me if I am looking for the maximum number from a sorted array. In best case, I will get that number after how many comparison? N comparison. In worst case also, how many comparison do I need? N comparison. That means, how do you represent complexity? To search any element in the sorted array, if you are looking for if this array is sorted in ascending order, if you are looking for any value, maximum value, then in best case you need to do N comparison. In worst case also what? You need to do N comparison. So if any algorithm is there where best and worst both are same, best is omega n and worst is, how to write worst? Worst can be written as big O n. Now in any case, if best case time complexity and worst case time complexity both are same, so how do you represent complexity of that particular problem? In spite of representing two different notation, I can represent theta n. Now this theta n is going to indicate that best case as well as average case, let's say worst case, both are same. So whenever best and worst both are best and worst both are same, we can represent that complexity with the help of what? Theta. This point is clear enough. Now we'll see what is best case, what is worst case through a graph. Why we are calling this asymptotic notation? We are trying to see the behavior of the algorithm under very extreme value of n. Now what is this graph? This graph is saying I have one algorithm. The complexity of that algorithm is defined, let's say, fn is equals to 3n plus 5. Same thing is written. This graph is saying fn is equals to what? 3n plus 5. This is the complexity of that algorithm. Now this algorithm is given to a developer. And what developer is going to do? Developer is going to implement this algorithm. Now during implementation, as a programmer you must be knowing, my algorithm may take this much time. While implementation, my number of lines may increase or decrease. That is the based on how developer is going to implement that program. So if this is my worst case means what? My program is minimum going to take this much comparison under worst situation. So this was the criteria decided that algorithm is going to take this much time under worst case. If you are not a good programmer, while implementation, you can increase number of line. You can say, once I am going to implement this, the complexity that I have received is what? 4n plus 10. 4n plus 10. So this was the ideal worst situation complexity. After implementation, the complexity has become what? 4n plus 10. So this complexity I am going to represent as g of n. Same diagram is given. This is the time complexity of the original algorithm, and this gn is nothing but the time complexity after implementation. Now if I have to compare these two complexity, how come these two are interrelated to each other? How they are, whether they are similar in nature? If they are similar in nature, can we write big O, omega, in which term we can represent? Now tell me one thing. If I am saying this is my worst situation, this is my complexity is worst, under worst situation my program is going to take this much time. If I am saying I can go daily in 5 hours in worst situation, this is worst. This is defined by, let's say, ideal definition. See, if somebody is taking 6 hours, that can also be considered as what? Worst. That means if I have declared something that under worst situation I am going to take 5 hours, anything more than that is always going to be worst. Anything more than that is always going to be what? Worst. That means if this is defined as a worst case complexity, anything more than that, this is called upper bound, and this is always going to be what? Worst case. Ideally it was defined this much. After implementation, complexity may increase. So if something is increasing from the given value, this is also treated as what? Worst case. Now how do you write same thing in mathematically? I can write, that means this was, Fn was the original complexity, Gn was the complexity after implementation. That means what I told you, that after implementation this value may increase. That means this Fn is always going to be less than or equal to C into G of n. C into G of n means what? After implementation the value can be this much. This value can increase. So this value is always going to be less than or equal to this. This point is clear. Now what is C? C can be any constant value which is greater than 0. Greater than 0. Now what is the meaning of this? Let me explain you. Why I have written, because this is most confusing thing. Mostly people used to remember this. What is the meaning of this? Let's say I have a program main. If the complexity of this program, there are two loops, I is equals to 1 to n. Then another loop is there, j is equals to 1 to n. Now how much complexity this program is going to have? Definitely what? 2n. Now how do you represent this complexity? This complexity you are always going to represent in this fashion, on. You are supposed to ignore this constant term. That means if any complexity is there, before that I can add any constant. This is not going to change, because this is how complexity is supposed to be calculated. Constant can be added. Why I am saying constant can be added? Let's say my algorithm is saying in worst case I am supposed to take order of n time. While implementation, number of line may increase, number of loop may increase, but the behavior of the algorithm should not go more than order of n. That means if I will say, tell me which program is better. In a program, complexity is there, say 3n, 5n, 7n, 100n, which program is better? All are exactly same, because whenever you are going to represent complexity, you will write order of n. So complexity wise, all programs are same. Same thing is written over here. This is the ideal complexity in worst case. Now after implementation, let's say complexity is g of n. So after implementation, number of line may increase or may not be. So what it can be, the actual complexities can be higher or equal to Fn. Same thing is written over here. The actual complexity can be higher or equal to Fn. If this is true, I can write Fn is equals to big O g of n. Now what is C? C is any constant value greater than 0, and n for any value of n which is greater than n naught and which is greater than 0. What is the meaning of that? I will explain you with an example. This point is clear enough. What is big O? Big O means if the ideal complexity is Fn, after implementation we are getting some other complexity. If this is defined as worst case complexity, so after actual implementation this complexity is always going to be less than or equal to the actual complexity. If that is the thing given, we can write Fn is equals to big O Gn. Let me take one example and then you can understand in a better way. So we'll have a detailed discussion about big O notation. Now what is N naught, I will explain you. Let's say Fn, that is original complexity or complexity of that algorithm is 4n, right? After implementation my complexity is coming, let's say n. Now can I write Fn is equals to big O Gn? Now what I told you, this can be only written if what? If I can prove, if this is a worst case situation, this big O representation is always going to tell you that this Fn is always going to be less than g of n. We can prove by taking any constant value and for any value of n which is going to be greater than n naught, and n naught can be greater than 0. Now what is the meaning of this? This can be written if we can prove this. Now let us try to prove this. 4n, what we need to prove? That 4n is less than or equal to n, c into n. Now tell me for which value of c this is going to be true. Let me take one. If I will take c is equals to 1, so this will become 4n. So this is not true. For any value of n, this is not true. If I will take c is equals to 2, so here I will have 2n. 4n is less than 2n, no. So I will not take this value. Let me take c is equals to 3. If I take c is equals to 3, can I prove this? No. So let me take another value, 4. Now you can see 4n is less than equal to 4n, and this is true. That means I can write, if we can prove that Fn is less than equal to c into g of n, then we can write what? Fn is equals to big O g of n, and we have proved that 4n is less than n by taking what value of c? By taking at c is equals to 4, this Fn is less than equal to c into g of n. That means I can write Fn is equals to big O g of n. This point is clear enough? I'll take sufficient number of examples so that this is going to be cakewalk for you. Let me take another example. Fn is equals to 4n plus 5. Gn is equals to, let's say, n. Gn is equals to what? N. Now we need to find out, can we write Fn is equals to big O of g of n? Under what condition we can write this? We can write this if we can prove that this Fn can be less than equal to c into g of n. Let me write the entire expression. Fn is what? 4n plus 5. Less than equal to what? N. By looking at my first reaction is what? This is higher than this one. But what we need to prove, is there for any value of c, can we prove this? So let me take one example. If I take c is equals to 4, if I take c is equals to 4, then this is going to be what? 4n plus 5 less than equal to 4n. This 4n plus 5 is the leading term. That means we cannot take c is equals to 4. You can understand if the left hand side is having 4n, the right hand side is minimum supposed to have 4n plus something. That means this should have which value? More than 4. So let me take 5. So 4n plus 5 less than equal to 5n. So c value we have taken what? 5. Is it true now? Let me check. If n is equals to 0, Please understand this. This looks, yes, that is done, but let me check this. 4n plus 5. Let me take a value of n here. I am writing here fn and g of n. If n is equals to 0, fn is going to be 5, gn is going to be 0. So fn is higher than gn. So this value is not possible. For n is equals to 0, this cannot be proved as true. Now take another example. N is equals to 1. So this is going to be what? 4 into 1, 4, plus 5, what? 9. And here we have 5 into 1, 5. So for n is equals to 1, still you can see fn is greater than gn. So this cannot be proved for n is equals to 1 also. Let me take n is equals to 2. If I take n is equals to 2, if I am going to replace that value n by 2, 4 2s are 8 plus 5, what? 13. And here I'll have what? 10. You can see still f of n is what? Higher than g of n. We cannot prove this. Now let me take n is equals to 3. If I take n is equals to 3, this is going to be what? 17. And this is going to be what? 15. Still cannot be proved. Now n is equals to 4. This is going to be 21. This is going to be 20. Still cannot be proved. N is equals to 5. This is going to be 25. And this is going to be what? 25. Now you can write, if we'll take n, I told you how to write this. This value of n naught is greater than equal to 5. So for any value of n which is greater than 5, I can prove that this is going to be 25, this is going to be 25. That means I can write fn is less than equal to c into g of n. What is the value of c? C is 5. So c into g of n. What is the value of c? 5. What is the value of n? That is n naught. N naught. What is, for which value of n this is true? Any value of n which is higher than or equal to 5, this is always going to be true. Fn is always going to be less than or equal to g of n. That means I can write fn is equals to big O of g of n. That's all. Let me take another example. By taking sufficient number of examples, you can understand this. There's no intelligence required. If two complexities are given, f of n, g of n, I can write f of n is equals to big O of g of n. This big O explanation means this complexity, this ideal complexity is always going to be less than this complexity. So if I am saying fn is equals to 3n, gn is equals to 5n, straight away you can say, since this complexity is less than this, I can straight away write fn is equals to what? Big O g of n. There is no doubt about it. Straightforward. Now if I take another example, fn is equals to n square, gn is equals to, let's say, 3n square. Do I need to prove anything? No. N square is always going to be less than 3n square. Directly I can write and fn is equals to big O g of n. That means whenever two complexities are given and you need to find a relation between this fn g of n, this is a what relationship? Less than equal to relationship. What relationship? Less than or equal to. Let me take one example. F of n is equals to 3n plus 7. G of n is equals to, let's say, 2n plus 2. 2n plus 2. Can we prove that this fn can be less than or equal to this? Let us try out. 3n plus 7. Here we have 2n plus 2. I told you while implementation, if we can prove f of n is equals to or less than equal to c into g of n, we can take any constant value. In the left hand side we have 3n, in the right hand side we have 2n. So this we need to take a proper value of c so that we can prove this. So what value of c we can take? We can take what? We can take, let's say, c is equals to 2. So this is going to be 4n. After that, if I'm going to take this, then 3n plus 7 less than equal to, this is going to be 4n plus 4. What value of c we have taken? 2. Now check whether this is going to be perfect or not. For any value of n greater than equal to 0, greater than or equal to 0, let me take n is equals to 0. N is equals to what? 0. This is going to give you what? Fn will give you 7. Gn is going to give you what? 4. So this Fn cannot be written as less than equal to c into g of n. For which value? N is equals to 0. Let me take another value. N is equals to 1. This is going to give you what? 10. This is going to give you what? 8. 3 into 1, 3 plus 7, 10. 4, 1, 4, 4, 4, 8. So this is not true. This cannot be written. This Fn cannot be less than c into g of n. Why? Because this is 10, this is 8. Now take n is equals to 2. If I take n is equals to 2, this will give me 13. This will give me 12. Still not true. Now let me take another value of n. 3. If I take 3, 3 3s are 9 plus 7, 16. 4 3s are 12 plus 4, 16. Now you can say 16 is less than or equal to, both are equal. Now we can write Fn is less than equal to c of g of n when c is equals to 2 and n is what? Greater than equal to 4. Then for all value of n which is greater than equal to 4, this is going to be true, and we can write what? Fn is equals to what? Big O of g of n. This point is clear? Now, theme of this story. Theme is what? If you are comparing two complexity Fn, g of n, if both are of same order, that means if you are comparing 3n with n, this we can anytime prove that this is less than this. Why? We can take a constant value, and after any interval of n, this is always going to be true. You can take c is equals to 4. This is true. So if you are comparing any two complexity and order are same means what? If Fn is 3n and Gn is n square plus 1, this can never be proved that this is less than this is. N can never be less than n square. Never. So this cannot be proved. But if you are comparing n, let's say 100n with 2n plus 5, we can prove that this can be less than this. Why? Because we have a liberty with number of constant can increase. We can take c is equals to what? Let's say 51, and that's all, work is over. This is always going to be true. This is always going to be less than this one. So moral of the story is what? If you are comparing two complexity and both are having same order, you can write directly without thinking anything in the competitive examination that Fn is equals to big O G, and this can be easily proved. No doubt about it. So if you are comparing two complexity of the same order, straight away you can write this much. Thank you very much. We'll see best case in the next class. Thank you.